Hello, and welcome to Lecture 8 for the course ECE 252B, Computer Arithmetic, Spring 2020. This lecture deals with Chapter 10 in the textbook entitled High-Radix Multipliers. So as I said at the end of the previous lecture, there are two main ways of speeding up multiplication over the simple bit at a time scheme, which takes k cycles for k by k multiplication. And the two classes of methods are reducing the number of partial products that need to be added so that we can add them faster. And that corresponds to doing multiplication in higher radiuses. And the second class of methods deal with adding those partial products as fast as possible. And those methods are represented by tree multipliers. Those are basically the fastest multipliers we can design. And also array multipliers that we'll deal with in the next lecture. So what is high-radix multiplication? It's basically doing multiplication in radiuses higher than 2. So this dot notation represents a 4 by 4 bit multiplication that we saw before. It's done by producing 4 partial products, each shifted by an appropriate amount, and then adding them together. Each of those rows of partial product is the product of one bit in x and the entire number a. So this is basically x0 times a. This is x1 times a. And it's shifted to the left because x1 is worth 2 units, whereas x0 is worth 1 unit, and so on. Now, the same dot notation diagram can represent a decimal multiplication. So this is a 4-digit decimal number. This is a 4-digit decimal number. This is the 8-digit product of the two 4-digit numbers. The only difference is that whereas multiplying one bit by a gives either 0 or a, okay, if this bit is 0, then 0 times a is 0. If this bit is 1, 1 times a is a. When you multiply a decimal digit by a 4-digit decimal number, the result will not be a 4-digit decimal number, but it can be 5 digits wide. So if this dot notation were to represent decimal, or in fact any higher radix multiplication, the partial products should be made wider by 1 digit. So those green dots that you see need to be added for this to accurately reflect decimal or other high radix multiplications. Radix 4, radix 8. There's just one exception, and I'll let you figure that out as a puzzle. There's only one other representation, radix and digit set, so that when you multiply two 4-digit numbers in that particular radix and digit set, the partial product will also be a 4-digit number. Okay, with that one exception, of course, binary, we already know it requires the same width partial product as the number a. A decimal, radix 4, requires this extra digit. There is one radix, and with some particular digit set, that does not require these these extra digits. Okay? It's in fact an end of chapter problem. I'll let you figure that out. So this is the multiplication recurrence with right shift written for a general radix R. It's very similar to the radix 2 recurrence, except that the 2 to the k that we had in the radix 2 recurrence has been replaced by R to the k. So A is pre-multiplied by R to the k, meaning it's left shifted by k digits. And then the right shift in radix R is basically dividing by R. Right shift in radix 2 was dividing by 2. Right shift in radix R is dividing by R. So the number 2 in the previous recurrence is replaced with R in both occurrences. And the rest is the same. So basically, once we form this partial product, we shift it to the right by 1 digit before adding the next one. We shift the sum of these two to the right by 1 digit before adding the third one, and so on. And multiplication with left shift is very similar to radix 2 as well, and this is the equation. Again, the left shift in radix 2 was multiplication by 2. Left shift in radix R is multiplication by R. Everything else is similar. Again, for the same reasons that we had for radix 2, multiplication with right shift is preferred. So here is radix 4 multiplication in dot notation. So at the top, you see the original 4x4-bit multiplication. When we do that multiplication in radix 4, basically what we do, we take 2 bits of x, which collectively represent the radix 4 digit, and multiply them by a to get this partial product. Notice that it is 1 radix 4 digit wider than a. And then we take the next 2 bits, or the next radix 4 digit multiplied by a. Notice that the second partial product is shifted by 2 bits with respect to the first one, or 1 radix 4 digit. Okay, so you see here that if we want to do this multiplication, we needed to generate 4 partial products in radix 2, and therefore add 4 numbers. When we do the multiplication in radix 4, we just generate 2 partial products and add them. That's basically a regular addition, adding 2 numbers. Whereas here, we need to do more to add 4 numbers. Now the only complication is that when you multiply a radix 4 digit by a, that radix 4 digit, let's say x1, x0, can be 0, 0, 0, or can be 1, 0, 1, or it can be 2, 1, 0, or it can be 3, 1, 1. Now 0 times a is easy, that's 0. 1 times a is easy, that's a. 2 times a is easy because that's basically a shifted to the left. But 3 times a is not trivial. You cannot easily form, if both of these digits, both of these bits are 1s, then you're faced with computing 3 times a. So over the next few slides, we'll see how we can handle this additional problem. Because if we solve this problem, then radix 4 multiplication, if, let's say, multiplying 3 by a can be done just as easily as multiplying 1 or 2 by a, we have managed to reduce the number of partial products by a factor of 2, and therefore making it simpler and faster to add them. So we call that 3 times a difficult multiple. And generally speaking, in high-radix multiplication, we sometimes have these difficult multiples. So for example, if you go to radix 8, the multiples that we will need will be 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, and 4 are simple multiples. 3, 5, 6, and 7 are difficult multiples that we somehow have to find out a way to handle them. Okay, so this is the first approach. Because 3 times a is a difficult multiple, we pre-compute, before starting the multiplication, 3 times a by performing this addition. So add a to left shifted a to compute 3 times a, store it in this register, and from that point on, any time that we need 3 times a, we already have it in that register, and it's just as easy to get it as the other multiples. So here is the rest of the multiplier. So the multiplier looks at 2 bits, the hardware of the multiplier looks at 2 bits of the multiplier, the operand, and these 2 bits control this multiplexer. If both bits are zeros, then 0 will be forwarded to the adder. If you have 0, 1, then a will be forwarded to the adder. If you have 1, 0, 1, 0, which represents 2, then 2 times a, basically shifted a, will be forwarded. And if we have 1, 1, then basically this value 3a goes there. So this solves the difficult multiple problem, 3a problem, by adding a cycle to the beginning of the multiplication. So the number of cycles, instead of being halved from k to k over 2, it's almost halved. It goes from k to k over 2 plus 1, where that one additional cycle is used to compute 3 times a and store it in this register. So we need an extra register in the multiplier. We need an extra cycle of computation time. But the rest of the process is almost twice as fast. So that's one way to do it. Here is an example of a radix 4 multiplication. So here is a at the top. Here is x. And in the middle, you see the pre-computed 3 times a that is stored in a register. As usual, we initialize the partial product to 0. Then we have x1, x0, basically 2 times a. This is 2 times a. Add, and then right shift. So because after right shift we have P1, the first partial product, I call this previous result, which is not yet shifted, 4 times P1. So adding those two numbers gives me 4 times P1. And then when I right shift it by 1 radix 4 digit, it gives me P1. Next, I look at x3, x2. That's 1, 1, which is 3. 3 times a is this value. So I just copy that here. Add. That's 4 times P2. And then right shift, that's P2. So to check this multiplication, I'm multiplying 6 by 14. This is 14. This is 6. The result should be 84. 84, which is 64 plus 16 plus 4. So that checks out. Okay, here's a second way of handling that difficult multiple. Whenever I have to add 3 times a to the partial product, so 0a and 2a as before, instead of 3 times a, which needs to be pre-computed and stored in a register, rather than adding 3 times a, I subtract a. Okay? Don't add 3 times a, but subtract a. That means I owe to the partial product 4 times a. Not only I did not add 3 times a, I subtracted a. So I have to add at some future time 4 times a. And 4 times a basically can be added in the next cycle by adding a. Because in the next cycle I will process the next higher radix 4 digit. Therefore, I remember this by storing a carry in this flip-flop. And that carry will be added to the next cycle. So if the next cycle this digit is 2, I will add carry and I'll basically deal with the digit 3, which is again basically subtract 1 and store a carry. If this is 3 and there was a carry from the previous cycle, this becomes 4. When there's 4, I basically add 0 and remember that there's a carry for the next stage. Okay, so I got rid of that extra register. I got rid of the extra cycle for computing 3 times a, but I lengthened the critical path in the multiplier. So the critical path starts from here, goes through this circuit, goes through this multiplexer, goes through the adder, and then back to the partial product register. So I've added this circuit on the critical path, and it may not actually be advantageous because what I've done, I removed 1 cycle from the processing time, but I lengthened every one of the k over 2 cycles by this amount, this logic. Needed to store the carry and then incorporate the carry into the next digit. So it's an idea. It may actually be advantageous under some conditions, but it's not obvious that it will be in all cases. Okay, and this is the truth table for mux control. So given xi plus 1, xi, and the carry from the previous cycle, c, this truth table tells me what inputs should be given to the mux and whether the carry should be set for the next cycle. I'll leave it up to you to study this table and convince yourself that it's correct. Now, we talked about Booth's recoding in the previous lecture. Modified Booth's recoding, or sometimes called Radix 4 Booth's recoding, it's basically the Radix 4 version of that recoding. Okay, so let me reveal before discussing that table. Here is the Booth's recoding example from the previous lecture, where zeros and ones in the binary number are replaced with zeros, ones, and negative ones according to the rules that we talked about. Okay, now if I take the original binary number and try to multiply it by something in Radix 4, here the digit will be 2, Radix 4 digit 2. This one will be 3, 2, 2, 1, 3. So there are several instances of 3. That is the difficult multiple. If I use this recoded version, let's see what happens. The recoded version has these digits. -2, okay, -1, -1, 0 is -2, 0, 0 is 0, -1, 1, this is -2 plus 1, that's -1. Doesn't have any 3 or -3. And the reason is obvious, because the recoded version of a binary number, the Booth recoded, never has 2 1s in a row, and it never has 2 -1s in a row. And therefore, the multiples that I need to form are all simple multiples. 0, 1, 2, those we already know are simple. -1, that's basically the complement of A. And -2, that's basically the shifted version of the complement of A. So if I use radix 4 Booth recoding, in other words, do the radix 2, and then take the number 2 digits at a time, the multiples that I get will be 0, plus or minus 1, plus or minus 2, all of which are simple multiples to form, and therefore I got rid of the 3, or the difficult multiple. Now, instead of doing the radix 2 recoding, as in the previous lecture, and then taking 2 bits at a time, I can do directly radix 4. So basically, the 2 digits will be xi, recoded by taking xi minus 1 into account, and xi plus 1 by taking xi into account. So these are basically the recoded versions of xi and xi plus 1. And this is basically the 2 of these taken together. So this table basically allows me to directly encode in radix 4. I take 2 bits of the operand, xi plus 1 and xi. I take a peek at the bit to the right. This is called the context of the recoding. And then, so if I see, for example, 1, 0 in these 2 positions, 1, 0, and then the context is 1, the multiple will be -1. If I see 1, 0, and the context is 0, the recoded radix 4 version will be -2. So these radix 4 digits are obtained directly from 2 bits of the operand x plus 1 bit of context to the right. So here is a numerical example of the multiplication using modified or radix 4 Booth recoding. So this is A, this is X, this is the Booth recoding of X. Here's something I forgot to explain last time. Let me explain here. Let's say these are 2's complement numbers. So A is positive, X is negative. What negative number is X? It's 2 minus 8, which is -6. And the recoded version of it is -1 in the 4's position, so that's -4, plus -2, so that's -6. So this Booth recoding, it turns out, and that's the thing that I mentioned I forgot to explain last time. When you get to the left edge of the number, okay, so whenever you have a string of 1s, like these 3 ones, the first of the 1s is replaced by -1. The other ones are replaced by 0s, and the first 0 to the left is replaced by 1. So 3 1s in a row are replaced by a -1 in the least position, and a 1 just beyond the highest position. Okay? Let's look at this one. Well, applying the same thing, this should be replaced by a -1. And then the 0, the non-existent 0 to the left, should be replaced by a 1. If this were an unsigned number, then I had to do that. If this is an unsigned number, and the most significant digit here is negative, this is a negative number now. Okay? I took an unsigned or positive number, turned it into negative. That's why I have to add that 1 to keep the magnitude of the number intact. But if this is a 2's complement number, I can stop right here, and I automatically get the correct value. Remember that this one is negatively weighted, so replacing it by -1 is the right thing to do. I don't need to extend the number. So for 2's complement numbers, Booth's recoding directly gives me the correct value of the number, which happens to be negative here. So if this is a 2's complement number, which is negative, this is also a negative number with the same magnitude. So that's why here you see that 1010, a 2's complement number, which is negative, is correctly recoded as a negative number. So the rest is simple. I have to take -2 and multiply it by a. So this is P0 initialized to 0. -2 times a is 2 times a complemented, which gives you this number. Add. See, I got a negative number here. Right shift by a radix 4 digit. That gives you P1, right shift. Then the next digit is -1 times a. It's again 1 times a complemented. Add. And you get the negative product after right shifting down here. Okay. So this is basically an implementation of that radix 4 recoding logic. The recoding logic looks at 2 bits of the multiplier, the 2 current bits that we are processing, plus the previous bit that we keep here. So as we right shift the multiplier by 2 bits, the next 2 bits to be processed appear here. The previous bit is kept here because I need that context as part of the recoding. So the recoding is done for xi plus 1 and xi, taking the context xi minus 1 into account. And then according to the table, the digit generated by this recoding logic is one of these 5 values: -2, -1, 0, 1, and 2. Now, because we have 5 values to encode, so the recoding logic has somehow to tell us which of these 5 values should be used. Now, for 5 values, I need 3 bits to encode them. I can't do it in 2 bits. And there are many possible 3-bit encodings of these 5 values. And this is a particularly good encoding. So what I'm doing here is I'm distinguishing between 0 and non-zero values. There are 4 non-zero values and a single 0. So this bit non-zero basically tells me if non-zero is asserted, I'm dealing with one of those 4 non-zero values. If non-zero is 0, then I'm dealing with the 0 value. Okay? And then the non-zero values can be negative or positive. So this neg signal tells me whether I'm dealing with a negative number or a positive number. And then in each category, I either have 2 or 1 as the magnitude. And this signal 2 tells me if it's asserted, means that the magnitude is 2. Otherwise, the magnitude is 1. Okay? Why is this a good encoding? Well, it turns out that with this encoding, I can multiply the digits, one of these 5 values, by the multiplicand A using just one multiplexer. How does this work? Well, non-zero is used as the enable signal to the multiplexer. If this bit is 0, the multiplexer is disabled and its output will be 0. And that's what we want to happen. If the multiple to be formed is 0 times A, we want the output to be 0. Okay? So for 0, we got the correct output. Now, if the magnitude is 2, we choose between A, sign extended by a bit, and 2A, which is basically a left-shifted A. So this is either A or 2A, depending on this signal. And finally, the negative, the sign, is taken into account by telling the adder that is not shown in this diagram to add or subtract. If neg is equal to 1, the adder will subtract. If neg is equal to 0, the adder will add. Okay, so with this clever encoding, I made it easy to multiply. First of all, this logic gives me one of these 5 values in this 3-bit encoding. And using those 3 bits, I can multiply the appropriate digit by A using this multiplexer, and also telling the adder to add or subtract. Okay, here is another way of taking care of that difficult multiple 3 times A. So we take the 2 bits, use xi to choose either 0 or A, depending on the value of xi, and use xi plus 1 to choose 0 or 2A, because remember, a bit in this position is worth 2 units. And then I have 2 values that collectively represent the product of these 2 bits by A. I add that to the old cumulative partial product, so I have to add 3 things. And I can do this, as we saw in the multi-operand addition chapter, by a carry-save adder and a regular adder. Okay, so the critical path, the adder, of course, is not shown, is down here. Before the adder, the path goes through a multiplexer. These 2 work in parallel, so there's just one multiplexer, a carry-save adder. Okay, so that's the multiple formation and then the actual addition. So let's compare this to the previous diagram. So remember, here we have a multiplexer and a carry-save adder. Here we have a multiplexer, like there, and the recoding logic. So this scheme will be faster if the recoding logic happens to be faster than a carry-save adder. It turns out that in most cases, and we can't prove this is highly technology dependent, but in most cases, this scheme is better because it's using multiplexers that are pretty easy to implement in CMOS. And carry-save adders are nothing but a bunch of full adders. And full adders are circuits that have been highly optimized over many years because they're such useful building blocks that people have come up with many designs that are fast, low power. So because this design uses standard, highly used building blocks, multiplexers, and full adders, it's more likely to be advantageous compared with this one because this requires this custom recoding logic, which is used nowhere else other than just for booth recoding. Okay, so it's likely, although there are exceptions, that this design is better. So we can use carry save adders to form those difficult multiples. Okay, but still in this radix 4 multiplication, we have cut down the number of cycles to k over 2 from k. We have added a little bit of latency to each cycle in terms of this carry save adder. The multiplexer, remember, was there even in the radix 2 multiplication. So that's nothing new. The carry save adder is the new element here. So the critical path of each cycle has been lengthened, and therefore each cycle will be slightly longer than the cycle for an ordinary binary multiplier. Can we do anything about this adder? Because the bulk of the cycle latency in a multiplier is this adder, because it involves carry propagation. Even if this is a fast adder, it still requires logarithmic time, whereas this is a constant time circuit, and the multiplexer is a constant time circuit. Okay, here's an idea for getting rid of the latency of that adder in every cycle except for the last one. So what we do, we keep the partial product in carry save form instead of just having one register. I'll explain in a minute why this carry save register has two parts in the upper half but only one part in the lower half. For now, ignore that fine distinction. So this is a carry save number. So that's the partial product up there. And this is the next number to be added, and that next number comes out of this multiplexer. It can be 0 or it can be the multiplicand. So this number is to be added to the carry save partial product, and the result can be kept in carry save form. So I don't use this k-bit adder in the intermediate cycle. I start with a carry save partial product, add the multiplicand or 0, and form the carry save partial product for the next cycle. So I iterate in this loop for k cycles, until I'm done with all the bits of the multiplier, all k bits of the multiplier. At that point, I convert this carry save partial product into a regular binary product by adding the two components. Okay, so here's what happens here. This is the carry save partial product. This is the next, remember that the next number is added to the upper half of the partial product. So the lower half, nothing is ever added to it. So that's why it's not kept in carry save form. It's just a regular binary number. And then when I add this carry save number to this third number, this is the carry save result, the sum bits in the same positions, and the carry bits beginning with the second position. And now, in preparation for the next cycle, I have to shift this partial product to the right. When I shift this to the right, this bit moves into the lower half, and all the other bits are shifted to the right by one bit. So this is the new carry save partial product. Here I got lucky because this bit that moves into the lower half is a single bit. If I had another bit here, then I would be in trouble. Okay. Fortunately, that bit is a single bit. It's just a sum bit in this position. The carry bits start here. Therefore, that bit just directly moves into the lower half. So the lower half that contained 2 bits up there now contains 3 bits, and so on. So this is a big improvement. Now I have k cycles of carry save addition. So the critical path for those cycles is this multiplexer and the carry save adder. Okay, so those cycles can be pretty short, the K cycles. But then I need one cycle at the very end that involves this K-bit addition that is longer. So instead of K long cycles, I have K very short cycles plus one long cycle at the very end. So this is basically multiplication by keeping the partial product in carry-safe form, which leads to major improvement in the speed of multiplication. I can use this carry-save idea with Booth multiplication. So here is the Booth multiplier where I have the Booth recoder box up there, looking at 2 bits of X and 1 bit of context. I decide what multiple of A should be added and form that multiple according to what we discussed before. And then the cumulative partial product is kept in carry-safe form. The 3 values are added. The cumulative partial product in carry-safe form is fed back up here. So I do K cycles, or K over 2 cycles, sorry, K over 2 because I'm doing radix 4, of carry-save addition, and then 1 cycle of addition. However, there is a complication here that we need to deal with. When I take the carry-save partial product and add the third number, and I get the sum bits and the carry bits, given that this is radix 4 multiplication, I have to shift to the right by 2 bits. When I shift to the right by 2 bits, this bit creates no problem because it's single and it just goes to the lower half. But these 2 bits in the next position create a problem because the lower half is supposed to be just plain binary. I don't want to have carry safe there. So these 2 bits cannot directly move into the lower half. I need to do something about it. The thing that I do is I basically take this 2-bit number and this 2-bit number, whose lower bit happens to be 0, this 2-bit number and this 2-bit number, and add them in a 2-bit adder. And when I add them in a 2-bit adder, I get a 2-bit sum. That's the part that moves into the lower half. And the carry. That carry I keep in this flip-flop. And so that carry is worth 4 units. I'm adding 2 2-bit numbers. The carry out of this position is worth 4 units. So I will incorporate it in the next radix 4 cycle. Unfortunately, in the next radix 4 cycle, there is an empty position here that is unused. And that position can accommodate the carry. So you see what comes into the lower half is a 2-bit number plus a 2-bit number that doesn't have a lower bit. Oops. Okay, so this is the 2-bit number. This is the 2-bit number. This is the 2-bit number that has just a higher position. And this carry from the flip-flop can go into that position. And then we add the 2 2-bit numbers. This is the 2-bit result that goes into the lower half of the partial product register. And the carry is kept for the next cycle. Okay, well, a 2-bit adder is pretty fast, so it doesn't lead to any slowdown in our process. Before the next cycle result comes around, so I feed back the carry save adder there, and I need another Booth recoding and another CSA, and that delay is more than long enough for this 2-bit adder to complete its job and be ready to accommodate the next pair of bits. Okay, now if I don't want to use boot recoding, okay, this diagram I think it's best left to describe when we deal with tree multipliers, parallel multiplication. I included it here in the textbook because this is where boot recoding is discussed, but I think it's better to discuss it later. So here is the other version of radix 4 multiplication using multiplexers. So the two multiplexers up here generate two numbers corresponding to these 2 bits of the multiplier. And let's say the old cumulative partial product is kept in carry safe form. So now I have to add 4 numbers. The carry safe partial product and the 2 multiples resulting from 2 bits of x. And we know how to add 4 numbers. We need 2 levels of carry safe addition. So now the critical path goes, remember that the carry safe result is fed back there in all but the last cycle. In the last cycle, we feed that through the adder. So in the regular cycles, not the final cycle, the critical path goes through a multiplexer, 2 carry safe adders. Okay, compare this with the boot version here. The critical path goes through boot recoder and carry safe adder. So there we had, in the other one, we had 2 carry safe adders and a multiplexer. So this boot recoder may actually turn out to be faster, but we don't know for sure until we actually implement this in a particular technology, circuit technology. Okay, so this is radix 4 multiplier using multiplexers to separate multiplexers to handle the 2 bits of x, and then adding those 2 numbers to the cumulative partial product in carry safe form. And again, because we are doing radix 4 shifts, we need this 2-bit adder in order to take care of the bits that are shifted into the lower half. So there's 2 levels of carry safe adders. Basically, it's an implementation of 4 2 counters. There are 4 inputs coming in and 2 outputs going out at the bottom. So we can use 4 2 counters, a bunch of 4 2 counters, to implement this instead of 2 carry safe adders. And 4 2 counters tend to be faster than 2 levels of carry safe addition. Okay, well, now that we have the basic method understood, it's a very simple extension to go to higher radiuses. So this is a radix 16 multiplier that handles 4 bits of the multiplier at once. So these are the 4 bits of the multipliers, xi plus 1, xi plus 2, xi plus 3. They're used to select 0 or a for xi, 0 or 2a for xi plus 1, the next 0 or 4a, 0 or 8a. So 4 values collectively represent the product of these 4 bits by a, by the multiplicand. And those 4 values must be added to the carry safe partial product. So 6 things have to be added. And from our discussion of multi-operand addition, we know that we need 3 levels of carry safe adders, or a bunch of 6 2 counters. Okay, 6 inputs, 2 outputs, and then these are fed backs. So the critical path now in each cycle is 3 carry safe adders, or 1 6 2 counter, plus these multiplexers. But the number of cycles is cut by a factor of 4. Instead of k, we have k over 4 cycles. Okay, so this is bound to be much faster, especially since we are using carry-safe partial product. So this is radix 16 multiplication. You may wonder why I skipped radix 8, right? It was logical to go from radix 4 to radix 8, where I handle 3 bits at once, then to radix 16. Let's see what happens if I go to radix 8. Oh, by the way, here we do a radix 16 right shift after one cycle. When I do radix 16 right shift, 4 bits move into the lower half. So you see at the lower right of the diagram, I have a 4-bit adder. I have a 4-bit adder to add these two 4-bit numbers, and this is 0. And then a carry is kept for the next cycle, and that carry basically fills that position in the next addition. Now this starting to be a little bit dangerous here, because a 4-bit adder may have a latency that is larger than the latency of one cycle here. Remember, one cycle here is 1 mux, 3 CSAs. A 4-bit adder may be slower. On the other hand, given that the output of this adder does not undergo any additional processing, it's just stored in a register, we can pipeline this adder, make it into a 2-stage pipeline if it's not fast enough. If it turns out to be not fast enough to keep up with the speed of this part of the multiplier, we can turn this into a 2-stage pipeline so that the rate at which we can feed operands into it increases to keep up with that, if needed. If it's fast enough to keep up with this part of the circuit, then fine, we don't need to do anything extra. Okay, so here is the radix 16 multiplier from the previous slide. What happens if I want to do radix 8 multiplication? How do I modify this? Well, think about this for a minute or two before advancing the video to my explanation of what happens if I go to radix 8, okay? So think about it. I'm going to reveal the answer. Basically, that multiplexer at the top must be removed. I need just 3 multiplexers because I'm handling only 3 bits of X. So that top multiplexer is not needed. And that carry save adder that is circled also is not needed, because now that that multiplexer does not exist, this number here does not exist. And therefore, these two values can be fed directly down here. I don't need a carry save adder. So I can prune the circuit by removing that multiplexer and this carry save adder to turn this into a radix 8 multiplier. Okay? However, notice that that radix 8 multiplier, the cycle time for that radix 8 multiplier is just as much as the radix 16 multiplier, because I still have 3 levels of carry save addition. Okay? So it doesn't buy me anything to reduce the radix from 16 to 8 and increase the number of cycles accordingly. Okay? So I might, if I go beyond radix 4, I might as well go to radix 16, because the cycle latency is the same. At least with this particular design, the cycle latency is the same for radix 8 and radix 16. And radix 16 has k over 4 cycles, as opposed to k over 3 cycles for radix 8. Okay, so this diagram basically shows what we have done so far on the left side. We took a regular binary multiplier that consisted of just an adder. The next multiple would be fed into the adder. The partial product is formed. So this partial product, if it's just in standard binary format, this adder has a high latency. If I use carry save partial product, then this adder will be a carry save adder in every cycle except for the last one. And by generating several multiples, so in radix 16 we generated 4 multiples at once and combined them with this carry save partial product in a small carry save adder tree, and then we iterated here until the last cycle. So this small CSA tree should be contrasted with the full CSA tree in parallel multipliers that we will see next time. So in full CSA tree, all the multiples. So if I'm doing a k by k multiplication in binary, there will be k multiples. All k of them are produced at once and then reduced in this tree, in fairly large tree. If I'm doing, say, 64 by 64 multiplication, there'll be 64 multiples coming here. And then this will be a fairly large, tall tree. And then I add these two numbers in the adder. So this is full carry save adder tree. This is a small carry save adder tree, which is an intermediate design, can be viewed as an intermediate design between this high cost, high speed full tree multiplier and the low cost, low speed regular binary multiplier. In fact, as I increase the radix, if I go from 16 to, let's say, 256, then I'll be handling 8 bits of the multiplier at once. So there will be 8 numbers here. So there will be 10 numbers to reduce. This will be a somewhat larger tree. Radix 256, I can handle 8 bits of the multiplier at once. So if the multiplier is 64 bits wide, I need 8 cycles if I go to radix 256. Okay, so depending on how large I make this CSA tree, whether I'm closer basically in spirit in the design to this end or to this end, 2 different names are applied to this multiplier. If I'm closer to this side, this is known as high-radix multiplier. So I handle 2 bits, 3 bits, 4 bits, even 8 bits at once. So that's called a high-radix multiplier. If I'm closer to this side, let's say I have 64 things here. Okay, instead of all 64 at once being fed into this tree, maybe I feed only 32 of them. So 32 go through the tree, emerge from this side, then the next 32. So I use the smaller tree with 32 inputs twice, 2 passes. In this case, I use this tree many times in high-radix multipliers. Okay, so basically, if I'm closer to this end, I tend to call this design a high-radix multiplier. If I'm closer to this end, basically I reduce this tree size as a cost-saving measure. And this was done all the time in older computers. Nowadays, hardware is so cheap that pretty much all high-performance microprocessors have this tree multiplier. So if I want to economize on this full tree multiplier, I call it a partial tree multiplier. If I want to increase the speed of this basic binary multiplier, I tend to call this high-radix. So high-radix and partial tree multiplier are really not different conceptually. It's just a matter of degree. To what degree I go to a method of handling several multiples at once. If it's a handful of multiples, then I call this a high-radix multiplier. If it's a whole bunch, maybe 16 or 32, then I tend to call this a partial tree multiplier. Okay, now the next concept to be discussed in section 10.5 is the concept of multi-beat multipliers. And in order to be able to explain that, I need to take a detour and explain how finite state machines or sequential circuits are built. From your course on logic design, you should know that any sequential circuit has a bunch of state flip-flops, one or more state flip-flops, and a next state logic that determines what should be stored in these flip-flops, what the next state should be, based on inputs to the circuit and the present state of the circuit. So the present state and inputs dictate what the next state should be, and this is synchronous. Every time the clock ticks, a new next state is computed and is stored in the flip-flop. So this diagram shows what's happened. When the clock goes high, the positive edge of the clock, then these inputs start affecting the contents of the flip-flops, and typically these are master-slave flip-flops, so that as their contents are being changed, the output remains stable. Because remember, the output of these also affects these inputs, so you don't want to make things unstable by allowing the inputs to affect the output, because that will be fed back and potentially make the circuit unstable. So the contents is being changed while the output is still the old value. Then on the negative edge of the clock, so these are typically negative edge triggered flip-flops, the change in the contents of flip-flop is reflected in the output. So basically during the positive edge of the positive part of the clock pulse, changes take place here, and this clock should be wide enough to allow signals to propagate through this next state logic and also have enough time to affect these changes. And then the change should be complete by this point, because at that point the new state will become observable at the output. The negative edge of the clock triggers the change in the output. So basically the circuit is not doing anything useful in this low part of the clock. During the high part of the clock, signals are propagating, flip-flop contents are changing, but at this point the change has already taken place and nothing happens until the next clock pulse. Okay? So in a way we can say we are wasting half. If these clock pulses are the same width for the high and low, we are wasting half of the time in doing nothing. So this design here, by duplicating the next state logic and duplicating the state flip-flops, we use latches now instead of flip-flops, allows us to operate twice as fast. So inputs come in, the next state is computed, the next state goes and changes these latches, in phase 1. Phase 1 is basically a clock pulse that corresponds to the high part of the clock pulse in the original design. And then during the low part of the clock, or phase 2, this next state logic computes the next state. So we take 2 steps in every clock cycle. 1 step during the high part of the clock, or phase 1, in this new 2-phase scheme, and another step advance during the phase 2 clock. Okay, so this can run twice as fast, but it also uses twice as much hardware. Both the next state logic and the state elements, the registers, are duplicated. Okay, so why is this relevant to multiplication? So here is a twin-beat multiplier constructed based on what we just discussed in the previous slide. There are 2 halves to the multiplier. Each half is a radix 8 booth recoded multiplier. So I take 3 bits of the operand and 1 bit of context, not shown here, and decide what multiple of the multiplicand should be added. And in radix 8, the multiples are -4, -3, -2, -1, 0, 1, 2, 3, 4. So the multiples go from -4 to +4. Of these multiples, all are easy multiples except for 3 times A and -3 times A. Okay? So this particular multiplier, the designer of this multiplier, decided to pre-compute 3 times A, store it in a register here. Once we have 3 times A, then whenever we need 3 times A, it's available to us. And here's A, and based on which we can form 2A and 4A. Those are base shifted versions of A. And then the negative versions of those are just complementations. So this logic here basically forms whatever multiple is dictated by these 3 bits and 1 bit of context, and forms that multiple using these 2 values, and adds that multiple to the carry-save partial product. Now, instead of storing, it stores the carry-save result here, but instead of using the same thing in the next cycle, it uses another copy of the circuit in the low half of the clock pulse, phase 2, to handle another 3 bits of the multiplier. So 3 bits of the multiplier are handled in the high part of the clock, phase 1, 3 bits in the low part of the clock. So this carry-save partial product is given to this half, which takes the next 3 bits. So these 2 registers are 3 bits out of phase. So this is, let's say, if this is x0, x1, x2, this is x3, x4, x5, the next 3 bits to be handled. Okay, so collectively these 2 circuits process 6 bits of the multiplier in 1 cycle. In 1 cycle of this radix 8 multiplier, they handle 6 bits. And then I have to do a right shift by 6 bits, therefore I need a 6-bit adder here. And then finally at the very end, I need a regular adder. Okay, so the idea is to do 2 3-bit chunks in 1 clock cycle instead of 1 3-bit chunk per clock cycle. And this works pretty well. It basically doubles the speed of radix 8 multiplication, so it corresponds basically to radix 64 multiplication, whereas the latency through the circuit is the same as a radix 8 multiplier. Okay, now this idea has been extended to 3-bit multipliers, but I'm not going to explain that. The reference is at the end of the chapter if you're curious to see how a 3-bit multiplier works. Okay, in this last section of the chapter, we talk a little bit about the VLSI complexity issues. A radix 2 to the B multiplier requires B times K 2 input AND gates to form the partial products, because we are multiplying B bits of the multiplicand by B bits of the multiplier by K bits of the multiplicand. So these AND gates basically do the multiplication. If we are using multiplexers, there will be B K-bit multiplexers. So basically order BK complexity for the multiple formation part, order BK area for the carry save adder tree, and at least theta K area for the final carry propagate adder. So this theta K is actually dominated by the BK. So the total area is B times K, order B times K. And the latency is given by this expression. Basically, we do K over B cycles, each of which takes log B time, that's the carry save addition, plus a log K at the end, that's the normal addition. Again, you can say that the log K is dominated by the other term, so it's order K over B log K for time. Now in VLSI complexity theory, I'm not going to discuss this or prove it. It has been proved that if you design multipliers, the area time product grows at least as fast as K square root of K. In other words, it's impossible when you account for all the circuitry, all the wires that you need to connect the circuits to each other and so on. Area multiplied by time grows at least as fast as K square root of K. So that's sort of like a cost effectiveness measure. So if you double the area and cut the time in half, that may be considered a worthwhile trade-off. Use twice as much hardware to have half as much latency. And then AT squared is another figure of merit. Here basically we are giving time more importance than area. So if you quadruple the area and cut the time in half, that is considered a worthwhile trade-off. Time latency is more important. And that AT squared measure must grow at least in proportion to K squared. In other words, you cannot design any multiplier whose AT is less than K squared root of K, order K squared root of K, or whose AT squared is less than order K squared. So how does our multiplier up there fare compared with these absolute minimums? Well, our AT, just take those two expressions and multiply them by each other. Our AT is order K squared log B plus BK log K. Most of the times the second term is dominated by the first one, so we have K squared log B instead of K square root of K, so it's way off. And then AT squared, again take the two expressions up there, multiply A by square of T, you get order k cubed divided by b times log squared b. Again, remember, b is much smaller than k in high-radix multipliers. So k cubed divided by b is more than k squared. And besides, we have that log squared b. Okay, so these multipliers do not get close to those absolute lower bounds. Still, they're very practical. And as I mentioned in the case of adders, these asymptotic analyses are interesting for complexity theory. But for numbers that we are interested in regular microprocessors, CPUs, GPUs, we are dealing with 32, 64, 128-bit numbers. They are not, asymptotically large. We are not dealing with many thousands or millions of bits. Although there are situations where we do those very wide multiplications in cryptography. But for normal arithmetic in CPUs and GPUs, these asymptotic results are not really all that relevant. Okay, so here in this table you see high and low radix multipliers compared. So when B is order 1, in other words, fairly small radix, then AT and AT squared are order k squared and order k cubed. When B is fairly large, it approaches k, the second column applies. And the last column is the optimal values that we discussed in the previous slide. So you see AT is smaller for low-cost, low-radix multipliers compared with high-radix multipliers. Okay, so what this tells us is that if we have a whole bunch of multiplications to perform, it is more cost-effective to include many small multipliers, many slow multipliers compared with one huge large multiplier. So we have a particular amount of real estate area on the chip. These slow multipliers use that area more efficiently, but then I can include maybe 10 of those, 20 of those to compensate for the low speed. These asymptotic results tell me that using a large number of these is more cost effective than using a small number of these. Okay, and I'm going to ignore that text inside the yellow box. We'll come back to it later. All right, so this is basically all I wanted to say about high-radix multipliers. In the next lecture, we talk about the fastest possible multipliers, which are tree multipliers and various design strategies for them, and also array multipliers, which are not particularly fast, but they have some other desirable properties that make them suitable for VLSI implementation. That's it. Bye for now until the next lecture.